Welcome back. We are going to be taking what we have learned about horizontal projectiles, which are the ones that have a velocity in the x direction, and then gravity causes them to start to fall. And we're going to take those two equations, expand upon them into something that is an angle projectile, something that is thrown up and then comes back down. So it's going to take on this shape right here. Instead of just starting here and pushing out and down, it's going to go up first and then back down, which means in order to get off the ground, we are going to have to bring back in a VIY, an initial velocity in the y direction. All right, so here we go. A quick review of what we learned last week. When you have a horizontal projectile, that Vx, if it starts at 20 meters per second, it remains at 20 meters per second the entire time. Right here, it's 20 meters per second. Right here, it's 20 meters per second. Right here, it's still moving at 20 meters per second in the x direction. Because it's constant, there's nothing slowing it down or speeding it up. In the y direction, it starts at 0. That initial velocity in the y direction begins at 0, but then it starts to increase as it falls, and that's due to the force of gravity. As things fall in the y direction, they increase their velocity. A quick reminder, the x always means horizontal. So Vx is horizontal velocity, and Vy, y always means vertical. It's moving in the up and down direction. All right, we had two equations that we could use. We could not swap them out. If you were working in the x direction, you had to use this equation right here. Because there's no gravity in the x direction, it remained constant. You could use this little equation right there. You cannot put y right here. If you are looking for height or delta y, you have to use this equation, and that is because gravity causes you to speed up as you fall, so it will need an acceleration, which is that negative 9.8. All right, as we move forward, the Vx in the shape of this type of projectile, this is called an angled projectile. It is shot or thrown up at some type of an angle. It goes up and it comes back down. The Vx, the velocity in the x direction, it doesn't matter at which part of the flight we are at, it still remains constant because we still neglect air resistance and there's no gravity in the x direction. Right? But that velocity in the y direction, that Vy, the push upwards, sometimes you are moving upward, sometimes you're at your peak, and sometimes it's falling downward, which means there's going to be a shift in the velocity in the y direction due to gravity. On the way up, the vertical velocity decreases. As something goes up, it gets slower until it hits the top, it hits the peak where the velocity equals 0, and then it starts to fall back down again, in which it increases. So if you look at this ball right here, as I throw it up, I give it an initial velocity in the y direction, I throw it up, it slows down till it hits 0, then it turns around, increases as it goes. All right, in this case, we're going to do the same thing, except we're going to give it a horizontal component. I'm going to walk in the x direction, giving a velocity in the x direction. At the same time, the y is going to decrease, hit 0, and come back down. It's just going to be spread out like this because of that velocity in the x direction. So as I go, we have just a slight horizontal projectile motion looking like that because it spreads out because of that velocity in the x direction. The actual velocity something leaves with. So let's say you hit a softball. The ball leaves at an angle, it goes up and it comes back down. The actual velocity that it leaves the bat with is a combination of, so here's the actual ball's motion, the velocity it leaves with, that is a combination of the x velocity, Vx, that's the velocity needed to move it side to side, and the y velocity, the velocity needed to get it up off the ground or off the bat. When you take those two and make it a combination, you get the actual velocity that the ball leaves the bat with. Okay, that is a mathematical formula, and we turn it into a triangle. It becomes, we can use the Pythagorean theorem and some trig in order to break apart the different velocities, because if you notice in our equations, we never have just v, we always have either vx or viy. We have to break those velocities into their different components. So the actual velocity that something leaves with is a combination of the velocity pushing in the x direction to move it side to side, and the velocity pushing in the y direction to get it off the ground. We just shift that over, turn it into a right triangle, and if we know the angle, we can find and break apart the different portions of the velocity. So a tennis ball is shot with an actual velocity of 20 meters per second. The actual velocity is always the hypotenuse. So I'm going to put the 20 right there. At an angle of 40 degrees north of east. So 40 degrees is going to be my angle. I want to find Vx and Viy, as those are what are going to go into the equations. So in order to do that, I'm going to use some sine and cosine. Check your calculator, make sure you're in degree mode. But if I have an angle and I have a hypotenuse, the opposite function gets me Viy, the adjacent function gets me Vx. So in order to find Vx, I would take the cosine of 40 degrees is equal to Vx over 20. The cosine of 40 degrees is equal to Vx divided by 20. To get the 20 off the bottom, you have to multiply it to the other side. So I'm going to multiply both sides by the 20. And then into my calculator, I just type 20 times the cosine of 40 degrees, and you should get a little over 15. I got 15.32. I go 2 decimals with the velocities when I use the trig. This is the Vx, which means that remains constant the entire time. So the entire time, the Vx is equal to 15.32. If I want to solve for the Viy, that is the sine function because it is the opposite over the hypotenuse. So the sine of my angle is equal to the opposite divided by the hypotenuse. I need to multiply that off the bottom, so times 20 on both sides, it cancels out. And if I take 20 times the sine of 40 degrees, I get 12.86. This would be the initial vertical velocity, 12.86. That is the initial velocity in the y direction. It then slows down, hits 0, and speeds up as it comes back down. So that changes throughout. Understanding the time, we can use a new equation. So if you look at your equation sheet, if you shift over from where you were, too many things in my hands, we were using Vx equals delta x over delta t and our delta y equation. If you go past the line to the next two, we're at the ay equation. So this equation is the a equals vf minus vi over delta t equation. We can use that to find time. It's going to become a third equation that we can use to help us find different variables. Okay, the only problem is it only works in the y direction. So we're just going to put little y's behind each of the different variables. Acceleration becomes ay, always negative 9.8. That's the only acceleration in the y direction. Vf becomes vfy, vi becomes viy, and then delta t remains delta t. There is one spot when you throw something up where it has a y velocity of 0, and that is at the top, at the peak. Right here, the vfy is equal to 0. All right, at that point, we can get rid of that variable from the equation because it's at 0 at this point, as long as we realize that when we use this equation to solve for time, we are right here. So the time that you're finding is the time at the top. That is perfect. If we're looking for height, the maximum height, that's always right there as well, delta y. So the time at the top is what we'll use when solving for delta y. But when we want delta x, all the way over here, the horizontal distance is this full distance over here. This time would only get us half of it. So we are going to have to be able to multiply our time by 2 to get the total time, the whole time it's in the air, when we're looking to solve for delta x. All right, so that's kind of a brief introduction to it. If you flip over your notes or go down to the next page, we're going to do an example together. All right, so notes on the angle projectile, second side. Up on the top, I have the equations that you're going to be using. These babies right here are on your equation sheet as well. So the key thing to remember, anytime you use this equation, in order to make this equal to 0, you have to be at the top. So the time that comes out of it is the time at the top, because that's the only place where the VFY is equal to 0 is right there. Okay, so at the 2017 Home Run Derby, ESPN put up a graphic and I took a picture of it. Said Miguel Sano hit a baseball at 26 degrees north of east with a velocity of 50.5 meters per second. Find the maximum height the baseball reached and how far it traveled horizontally. Okay, so the actual flight of the ball looks like that with an angle of 26 degrees, and it left with an actual velocity of 50.5 meters per second. I just took all those numbers off of the graphic that ESPN put up there. At the moment of impact, right here, that 50.5 meters per second, some of it is the velocity in the y direction in order to get it off the ground, and some of it is the velocity in the x direction in order to push it outward so that it becomes a home run and it goes over the fence. All right, what we have to do is we have to use trig in order to break apart how much of the velocity is in the y direction and how much of it is in the x direction. So at this moment of impact, we can turn it into a triangle, right? The baseball doesn't move in a triangle. We are just taking one moment of time and we are taking the math in order to use the triangle to solve for and break apart the different velocities. So the hypotenuse is always the actual velocity, and then the angle was 26 degrees. We are going to use sine and cosine in order to solve for VIY and VX. I'll start with VIY. It is opposite, and I have a hypotenuse. That is sine. So the sine of 26 degrees is equal to opposite over hypotenuse. I need to multiply this off the bottom, so I take 50.5 times the sine of 26 degrees. I go to 2 decimals, so I got 22.14. It would be meters per second because it's a velocity. So the velocity initially in the y direction, the velocity pushing the baseball upward, is 22.14. From here, in order to find how much of the velocity is used to push the ball outward, I need to find Vx. It is the adjacent, which means I have to use cosine. So cosine of 26 degrees is equal to Vx over 50.5, adjacent over the hypotenuse. I multiply off the bottom, so I take 50.5 times the cosine of 26 degrees, and I find that to be 45.39 meters per second. So when you look at the different velocities, a lot of the velocity is being used to push it outward and not as much using to push it upward. So it's not going to be as high, it's going to be longer when we end up solving for those. So Vx is 45.39. All right, this equation right here, in order to find maximum height, delta y, we have to use that equation. To find total distance, delta x, we have to use that equation. Both of them need the time. So in order to find the time, we're going to use this new equation we just came up with. Same as before, except with little y's behind it to show it only works at the y. And we're going to use that equation to find the time at the peak. So in the motion of the flight of the ball, it will find us the time right here, because that is the only place where the VFY is equal to 0, so that's the only place that variable can disappear. All right, AY is always negative 9.8. So we're going to have AY, negative 9.8, equals VFY is 0, minus VIY, I just solved for it, 22.14, so I have a number to put there, over delta t. In order to get that t off the bottom, I have to cross multiply. So I have to take t times the negative 9.8, so I get negative 9.8 times t, and I set that equal to the other side, which is just a negative 22.14. I divide by negative 9.8, it crosses out, and I find that t, when I plug it in, 22.14, divided by, both of them are negative, the negative 9.8, and I get the t is 2.26 seconds. That is the time right here at the top, because that is the only place that this equation works, because that is the only place where one of the y velocities is equal to 0. All right, if that's the time at the top, that's halfway through. In order to find the full time, all I have to do is multiply it by 2. So if I take 2.26 and I multiply it by 2, I get 4.52 seconds. All right, so delta t is 2.26 seconds. This is the time at the top. So the total time is 4.52 seconds. Now I have to keep those two times in mind when I go to find delta x and delta y. All right, maximum height. That is right here. That is at the top, which means I want the time at the top. That means I need to use the 2.26 as my time. So delta y equals VIY. Back to the beginning, up kind of at the top of the notes. VIY, we solved for it. It was 22.14. Times delta t, 2.26. Plus 1/2. Gravity is a negative 9.8. Do not drop out that negative. Times your t squared, which is 2.26 squared. Do your math individually. If you don't get this typed into your calculator easily, take this times that, and you get a little over 50. I got like 50.03. Plus, if I take this times this squared, I get 25.02 negative. That means this, because it's a negative, has to subtract away from that, and I find that my delta y is approximately, with a couple of decimals, and it'll be different for different people as you round differently with your times, it should be approximately 25 meters. All right, so if you change that into feet, that'd be about 85 feet or so. 100 feet, kind of in that range. That's how tall the ball went, how high. All right, last step. I want to find the total distance that the ball traveled. Total distance, delta x, would be how far away from home plate the ball ended up. That is all the way over here. I don't want a time right here. That would only get me halfway. I want a full time. So I have to use the 4.52 for my time for this one. Vx, I solved for it up above. It was 45.39. So Vx, 45.39 equals delta x over the full amount of time. So you have to use 4.52. You have to multiply it off the bottom to the other side. So multiply both sides by 4.52, and you should find that delta x is approximately, you'll have different decimals, it was a little over 205 meters. So I just rounded to 205 meters. If you kept the decimals, that is just fine. All right, so just to quickly recap, the difference between a horizontal projectile, one that just pushes out and goes down, which we did last week, and an angle projectile, one that goes up and back down, is that in order to get off the ground, you have to have an initial velocity in the y direction, and we didn't have that before. So a VIY comes back into play this week, and we can use the angle that something is shot at and the actual velocity to find the x and the y components of velocity. And that is because, once again, the actual velocity of a ball leaving a bat is a combination of the y velocity to get it off the ground and the x velocity, Vx, to push it outward. All right, that is a mathematical function of a right triangle, so we can use sine, cosine, and Pythagorean theorem in order to help us solve for those. So I hope that this goes well for you. I will put hints up on some of the assignments for you. And then I have a little small lab for you to look at, a small video to look at to get data for the lab. So good luck. Make sure you send me questions if you get stuck.